Okay, last and definitely not least, we've got Dylan Herman talking about quantum optimization. I'm really excited about this work, so please, hopefully you do a great job because I think it's rad.
Did they not mic you? This, will this work? All right, that'll work too.
Yep.
So today's talk will be on speedups for convex optimization via quantum dynamics. So just kind of an outline of the talk. I'll start with more stuff on simulation, which will of course be interesting given the simulation conference. And then I'll talk about something a little bit different, which is around convex optimization, which hopefully will be maybe new for some of the people in the audience, and then how we use these results on simulation to solve convex optimization problems. So given the many physicists in the audience, probably one of the most fundamental equations in quantum physics is, of course, the Schrodinger equation, the one that involves a momentum plus a potential type term. And so one of the things we wanted to study was to understand what is the cost of simulating this equation on a digital quantum device, given that you'll see here that x is over the real numbers, d here, which is the dimension of the system in terms of how many spatial dimensions there are, is allowed to vary. And we want to understand how can we simulate this on a digital quantum device. And one thing that may not be immediately apparent is that this is also potentially very useful for solving optimization problems. So a simple algorithm is to just say, OK, f here is some function that you want to minimize. In this setting, it's an unconstrained problem. And you want to find the x that minimizes f. And so you could plug it into your Schrodinger equation and solve this, sort of run this on your digital device for a period of time, and you'll get some quantum state, and then you measure the quantum state in the position basis. And the hope is that the expectation and position basis will be close to the minimum, and then you can use something like Markov's inequality to show that with a constant probability, you will measure something that is close to the minimum, repeat it a few times, and then you can exponentially boost this probability. And so you also want to understand how well does this do as an optimization algorithm. So the first result will be around, two main contributions. So there has been some existing work on the digital simulation of Schrodinger equations. So this specifically this collocation result by Childs and others. And this is what we used for simulating this algorithm, or for simulating the Schrodinger equation. However, for us, we want to have a general asymptotic result. So we require making sure, one, that this simulation algorithm can work in arbitrary dimensions. So here, d, which is the number of spatial dimensions, needs to be able to go to infinity or be very, very large. And so we want to kind of have a better understanding of this algorithm and get an end-to-end complexity, such as spatial resources in terms of qubits, and also bound some other terms that were potentially unbounded in their paper, because you want to actually provide a rigorous speedup. And the algorithm we will be utilizing for solving optimization problems, which is basically simulating this Schrodinger equation you saw before, is the result by Lang et al., which is this quantum Hamiltonian descent algorithm for unconstrained optimization. So to start, this is our main simulation theorem, which extends the results of Childs and others, which is that if you have a continuous Schrodinger equation here in real space, and the one thing we require, which for our particular application of optimization is not a big deal, maybe a bigger deal in other physics applications, but we assume the potential can be truncated. So we truncate this potential, And then from there, you can now solve this, simulate the evolution on a digital quantum device. And you are producing this effectively proxy state. This state is a quantum state that is over a grid. So you take your real space, you chop it off, and you create a hypercube. And in this hypercube, you now consider a certain number of grid points. Let's say n to the d grid points. You have n spacing per dimension. And you can basically simulate the equation. So here we provide one is the query complexity, which is the total energy throughout time. So this is lambda L1 into L1 norm of B, which is lambda is a bound on F throughout the entire hypercube. And the main thing we also looked at is figuring out the number of qubits required. So you require on the order of d squared qubits to they're sufficient to discretize. And lastly, our guarantee is we provide a closeness on the outputs of observables that you get from the proxy state and the actual state. So you'll see one is a discrete sum, the other is integral, and you provide a closeness result on this. And so as I mentioned, we utilize this what's called collocation approach or pseudospectral collocation approach, which is you effectively truncate your Hamiltonian in Fourier space. This gives you now a truncated Laplacian whose Fourier spectrum has been truncated, and your potential is now evaluated on a grid. And then from here, you now have a discrete Hamiltonian, which you can now apply existing Hamiltonian simulation algorithms. Particularly, we choose this rescaled Dyson series approach or interaction picture simulation. The benefit of this is that you now switch to the evolution picture of the Laplacian, which avoids this potential blow up with discretization spacing. So for example, Laplacian here, with this normal blow up with your number of grid points you take, whereas the potential remains potentially bounded, as we assume this is a bounded function. And so here, as I mentioned, we extend the existing analysis to bound certain parameters that are left unspecified. And so here, as I mentioned, we have this truncated version of potential. We define this thing called R restriction, which is effectively just truncating potential to some R length hypercube. And this gives rise to one is a qubitized state. So we have here, this is a digital state, which is defined by a sequence F, which is it maps, of course, points on this n to the d grid to complex numbers. And then we have what is called the Fourier interpolant, which is a way of continuously extending discrete sequences and comes from signal processing, which is effectively the lowest degree Fourier polynomial that interpolates this discrete sequence. And so when we do analysis, we work with this continuous extension, but in reality, you get this discrete state. And the actual output of the algorithm is bounding the difference between the actual continuous wave function in real space and its interpolant. And then from there, you can do just discretization analysis like Riemann sum analysis to bound the error on this state. And so this is effectively what we get. This is bounding the evolution between what, as I mentioned, the Fourier interpolant. So here we have phi is the true solution of the Schrodinger equation in real space. Psi is going to be this interpolant. So you take the discrete wave function you get, you interpolate it in Fourier space to get the lowest degree Fourier polynomial that approximates it. And now we can bound the L2 distance between them. One thing that is worth noting is that this depends on what are called Sobolev norms, which effectively, in a sense, measure the amount of, the amount of, let's say, the second Sobolev norm, in a sense, measures some sort of kinetic energy. And higher Sobolev norms measure sorts of regularity. And so here you'll see that, for one of these terms here, it's like the nth Sobolev norm. And unfortunately, in our setting, because we're working in a very high-dimensional optimization problem, we need m to go with D. And Sobolev norms here are meant to capturing a phenomenon known as aliasing, which occurs in signal processing, which comes from the fact that you are, in a sense, sampling at a discrete number of points. And so in Fourier space, the spectrums overlap, and you get mapping of higher frequencies to lower frequencies. And so, yeah, so to kind of go through a little bit of the optimization, how much time do I have? I just wanted to mention one quick thing then. So yes, we have d squared as number of qubits. This comes from the fact that we have the Sobolev norms grow, unfortunately, horrendously as d to the d squared, but because because we take the log, we get d squared qubits. This was done through, in effect, a technique called as mollification, which is a smoothing procedure that smooths the wave function. So convex optimization. So this is the formulation of a general convex black box optimization problem in which you have some function f, and you're given access to an oracle, which we call a p-th order oracle, which gives you so it's a 0th order oracle will give you evaluations of the function So you give it x, it gives you f of x. You have a first order oracle, which will give you the gradient, or in what's called the non-smooth setting is the subgradient, which is, for I guess brief, is basically something that kind of acts as a supporting hyperplane to the function. And of course, as you have higher order smoothness, you get higher order derivatives, you have second order methods, and so on. And the goal is to minimize this convex function given some initial point in, let's say, an L2 ball of radius r. And classically, in the setting in which you are only given access to a gradient or subgradient, the best algorithm is what is known as projected subgradient descent, which is, you can think of it as gradient descent, although it has some caveats in the sense it does not actually converge. You have to do some sort of averaging of the iterates. And this is a well-known algorithm. And more recently, in recent years, Van Apeldoorn and Chakrabarty initiated the study of optimization with quantum oracles. And unfortunately, though, this above rate, which is going to be gr over epsilon squared, so g is Lipschitz constant of your function, is optimal in both quantum and classical settings. But this is but the important point is the classical algorithm is using first order access. It is given access to subgradients. But what if we were given only zeroth order access? So it is known that recently the quantum subgradient algorithm, which uses Jordan's gradient computation algorithm, can achieve the same rate but with zeroth order queries. And recent work is, but however, classically it is only known to do this with a D dependence. So here there's this magical black magic algorithm known as Nesterov's accelerated gradient descent that was able to, in the setting in which you have smooth gradients or gradients for Lipschitz, you can utilize something that's somewhat like momentum, although that's not necessarily the correct analogy, but achieves you'll see it's 1/4 faster than the previous rate. However, in the smooth setting, gradient descent achieves 1 over epsilon, so it's quadratically faster in the smooth setting. And because you've introduced something like momentum, you can have this kind of dynamical picture in which you get a classical Hamiltonian system, which shown via this Lyapunov argument can actually converge at any rate you want, which we'll get to why that's not true in reality, but in this system you can converge at any rate. You'll see omega can be tuned to be as fast as you want. And Lang et al. Worked on in developing quantum Hamiltonian descent, which is a first quantization of this previous system. So now you arrive at a Schrodinger equation. And so here we can prove something very similar, which is we have a similar Lyapunov rate and a guarantee on the expectation of the function value in position space, which again, Markov's inequality will give you the guarantee on observing the minimum. And again, we can pick any rate we want. Well, how can we not solve optimization problems instantaneously? That's because we are bounded, and when we do a digital simulation, we have to pay an amount that scales with effectively energy. So you have this interesting trade-off where you can actually go as fast as you want, but you pay in more queries. So as you see, as you increase k, so you get a faster rate, you're paying more in queries in the end. So the actual query complexity is this L1 norm of B. So you actually, to understand the actual quantum query complexity of the quantum algorithm, you have to study the discrete version here. And dynamical approaches have been shown to be more robust than existing gradient methods. And so here we have our result on the query complexity of QHD. This is made possible by our previous simulation algorithm, the theorem 2.1, which shows how many qubits we need, et cetera. And here we have d to the 3 over 2. The important point is, as you may have seen earlier, I showed that a classical algorithm can solve this problem with d. However, we'll get to later that this actually turns out to be, the quantum is faster in certain settings. This additional d to the 1/2 term comes from the fact that when we're simulating the quantum dynamics, we're currently stuck to a box. And because in this setting, the norm over the box can be square root d larger than it can be over, let's say, the L2 ball, we're kind of paying this additional square root d factor that we can't get rid of. But additionally, the overall d dependence, necessary d dependence in the algorithm comes from effectively a Heisenberg uncertainty principle. The fact is that if let's say you must have some sort of d dependence, because here, if you're going to tightly concentrate the wave function, you're going to increase its momentum by d, and you're going to pay this effective d factor. And so when we do this Lyapunov argument, an important point is that there are hidden dimension-dependent factors here that depend on the initial value. And so yeah, and unlike classical, quantum here does not appear to benefit from gradient Lipschitzness. So I guess to get to I'll skip this slide because there's no speed up here, but for here we actually gain a speed up from this algorithm due to noise robustness in the stochastic setting. So in the stochastic setting, you effectively get, you can think of it as like training neural networks. You're given random gradients, and you want to average the gradients together to minimize the function. So in our setting, because of this, even though we paid a d-dependence more than classical, the effect of the noise robustness benefit the algorithm. So we have a speed up in D in this setting. And so yeah, that's it. Thank you.
Great. Thank you very much for an awesome talk. Questions? Silence. Okay, so then I guess one question that I've got for this is in terms of the convexity that you've got. Often, these results you require strong convexity in order to be able to prove. Can you talk a little bit about what you would end up doing in order to be able to use these results in a situation where you don't have strong convexity?
Yeah, very good question. So in this setting, we don't require strong convexity. So in this setting, it works in the non-smooth setting, so always assume as the function is convex in Lipschitz. And it seems at least one thing we've seen is it's hard to take advantage of more structure. Potentially for strong convexity, you can use different Lyapunov function to get slightly better rates, so there's hope in that setting. But yeah, so currently here it's completely non-smooth. There's no more assumptions. Unfortunately, it appears that the quantum algorithm cannot take advantage of, let's say, gradient smoothness, which we go from projected gradient descent to Nesterov's algorithm, which is a fourth faster, basically. So like we're trying to understand how can we make better use of that. So it'd be nice, let's say, have simulation algorithms that do better when, let's say, the potential has gradient smoothness. Hopefully that answers your question.
Any other questions?
Yeah, thank you for the talk. Can you comment a little bit more on the non-smoothness and maybe some intuition why this quantum case cannot take advantage of higher order gradients?
Yeah, very good question. So just to clarify, when we say non-smooth here, we mean that the function is gradient. So either the function may not be differentiable, in which case we have subgradients, or the function may be differentiable and the gradient does not have a finite Lipschitz constant. So what I mean by smooth and non-smooth here. And why we can't take advantage of it. So one is at least when doing the QHD analysis. So for example, this the Lyapunov argument I mentioned here. One thing that's kind of hidden in here is that, actually I wish I kind of had it. But the dependence is effectively, here you're going to have a term that's going to end up being like the norm of the function across kind of the entire space. And there you can kind of directly insert things like Lipschitz constants. But the fact that it depends on, let's say, the total energy here, it's not clear how to insert. You can kind of arbitrarily insert smoothness, like because if a function is G Lipschitz, so you have a bound on its total. Let's say it's G Lipschitz on a ball of radius R, you can insert a bound of GR. If it's gradient smoothness, you can insert LR squared, but you're kind of artificially inserting this. And also these effectively, the simulation algorithms themselves also depend on the norm of this. So the norm of the energy here, which is again bounded by the total, the infinity norm of the function over the whole space, which is only GR. So in a sense, like in the quantum algorithm itself only requires zeroth order queries as well. So I guess kind of rough answer, I guess the algorithms themselves are only relying on zeroth order queries. And also this, like the Lyapunov argument here, it's kind of challenging to insert other assumptions. I mean, one thing we could potentially do is like strong convexity, which is not necessarily inserting smoothness in the gradients, but using the fact that it has lower bounded by quadratic. But yeah, roughly it's because if you look at the initial analysis, this algorithm depends on just the norm of the function. And as you see here, one thing you could think about doing is that if you look at, let's say, commutator scaling, you get terms that, let's say, involve Laplacian times commutator with f, and maybe you get some sort of Lipschitz type thing. But given the fact that you now have Laplacian and f, classically these algorithms depend on the norm of the Hessian, but this gives you d times norm of the Hessian, so this would not help. So yeah, kind of roughly an answer. Hopefully that answered your question.
Okay. Any further questions? All right, well, I'll bug the author with one. Okay, maybe not then. Oh, no, sure.
I'll ask him later.
All right, cool. So, great. One other thing I wanted to ask about this is our work on the dynamic approaches, we ended up finding that one of the major concepts for us that was important was the condition number of the Hessian. So I would kind of imagine there'd be a similar concept that would end up popping up in your analysis. What's the analog that ends up showing up here, and if there isn't one, why?
So here, that's a good point. So I guess kind of just in terms of the actual, let's say, forgetting about the discretization, the actual like continuous time convergence here, this in a sense will only depend on effectively the total energy. So it'll be integral of this term over time. And so here, you're bound to affect the only properties of f it depends on are effectively its infinity norm over the whole box. And so it's, yeah, so in this, I guess, I mean, we're not taking advantage of the fact, let's say it's like harmonic oscillator-like or anything, which we're not really, I think the analog here would be just the Lipschitzness. So here, this algorithm, and again, you get a worse rate too. So like, because it's not Schrodinger, so if it were Schrodinger convex, well, if it were Schrodinger convex and smooth, you can get a faster rate. But here, what you pay also is the rate is a lot worse. So even, for example, if the problem is smooth or smooth and Schrodinger convex, this algorithm still only is 1 over epsilon squared. So I think that is roughly the you pay.
Okay, wonderful. Thank you very much. Let's thank the speaker one last time.